Fire is the rapid oxidation of a material in the exothermic chemical process of combustion, releasing heat, light, and various reaction products. Slower oxidative processes like rusting or digestion are not included by this definition. Fire is hot because conversion of the weak double bond in molecular oxygen, O2, to the stronger bonds in the combustion products carbon dioxide and water releases energy. The bond energies of the fuel play only a minor role. Here, at a certain point in the combustion reaction called the ignition point, flames are produced. The flame is the visible portion of the fire. Flames consist primarily of carbon dioxide, water vapor, oxygen, and nitrogen. If hot enough, the gases may become ionized to produce plasma. Depending on the substances alight, and any impurities outside, the color of the flame and the fire's intensity will be different. Fire in its most common form can result in conflagration, which has the potential to cause physical damage through burning. Fire is an important process that affects ecological systems around the globe. The positive effects of fire include stimulating growth and maintaining various ecological systems. The negative effects of fire include hazard to life and property, atmospheric pollution, and water contamination. If fire removes protective vegetation, heavy rainfall may lead to an increase in soil erosion by water. Also, when vegetation is burned, the nitrogen it contains is released into the atmosphere. Unlike elements such as potassium and phosphorus which remain in the ash and are quickly recycled into the soil, this loss of nitrogen caused by a fire produces a long-term reduction in the fertility of the soil, which only slowly recovers as nitrogen is fixed from the atmosphere by lightning and by leguminous plants such as clover. Fire has been used by humans in rituals, in agriculture for clearing land, for cooking, generating heat and light, for signaling, propulsion purposes, smelting, forging, incineration of waste, cremation, and as a weapon or mode of destruction. Physical properties. Chemistry. Fires start when a flammable or a combustible material, in combination with a sufficient quantity of an oxidizer such as oxygen gas or another oxygen-rich compound, is exposed to a source of heat or ambient temperature above the flash point for the fuel-oxidizer mix, and is able to sustain a rate of rapid oxidation that produces a chain reaction. This is commonly called the fire tetrahedron. Fire cannot exist without all of these elements in place and in the right proportions. For example, a flammable liquid will start burning only if the fuel and oxygen are in the right proportions. Some fuel-oxygen mixes may require a catalyst, a substance that is not consumed when added in any chemical reaction during combustion, but which enables the reactants to combust more readily. Once ignited, a chain reaction must take place whereby fires can sustain their own heat by the further release of heat energy in the process of combustion and may propagate, provided there is a continuous supply of an oxidizer and fuel. If the oxidizer is oxygen from the surrounding air, the presence of a force of gravity, or of some similar force caused by acceleration, is necessary to produce convection, which removes combustion products and brings a supply of oxygen to the fire. Without gravity, a fire rapidly surrounds itself with its own combustion products and non-oxidizing gases from the air, which exclude oxygen and extinguish the fire. Because of this, the risk of fire in a spacecraft is small when it is coasting in inertial flight. Of course, this does not apply if oxygen is supplied to the fire by some process other than thermal convection. Fire can be extinguished by removing any one of the elements of the fire tetrahedron. Consider a natural gas flame, such as from a stove-top burner. The fire can be extinguished by any of the following: turning off the gas supply, which removes the fuel source, covering the flame completely, which smothers the flame as the combustion both uses the available oxidizer and displaces it from the area around the flame with CO2. Application of water, which removes heat from the fire faster than the fire can produce it, or application of a retardant chemical such as halon to the flame, which retards the chemical reaction itself until the rate of combustion is too slow to maintain the chain reaction. In contrast, fire is intensified by increasing the overall rate of combustion. Methods to do this include balancing the input of fuel and oxidizer to stoichiometric proportions, increasing fuel and oxidizer input in this balance mix, increasing the ambient temperature so the fire's own heat is better able to sustain combustion, or providing a catalyst, a non-reactant medium in which the fuel and oxidizer can more readily react. A flame is a mixture of reacting gases and solids emitting visible infrared, and sometimes ultraviolet light, the frequency spectrum of which depends on the chemical composition of the burning material and intermediate reaction products. In many cases, such as the burning of organic matter, for example wood, or the incomplete combustion of gas, incandescent solid particles called soot produce the familiar red-orange glow of fire. This light has a continuous spectrum. Complete combustion of gas has a dim blue color due to the emission of single-wavelength radiation from various electron transitions in the excited molecules formed in the flame. Usually oxygen is involved, but hydrogen burning in chlorine also produces a flame, producing hydrogen chloride. Other possible combinations producing flames, amongst many, are fluorine and hydrazine and nitrogen tetroxide. Hydrogen and hydrazine (UDMH) flames are similarly pale blue, while burning boron and its compounds, evaluated in mid-20th century as a high-energy fuel for jet and rocket engines, emits intense green flame, leading to its informal nickname of Green Dragon. The glow of a flame is complex. Blackbody radiation is emitted from soot gas and fuel particles, though the soot particles are too small to behave like perfect blackbodies. There is also photon emission by the excited atoms and molecules in the gases. Much of the radiation is emitted in the visible and infrared bands. The color depends on temperature for the blackbody radiation, and on chemical makeup for the emission spectra. The dominant color in a flame changes with temperature. The photo of the forest fire in Canada is an excellent example of this variation. Near the ground, where most burning is occurring, the fire is white, the hottest color possible for organic material in general, or yellow. Above the yellow region, the color changes to orange, which is cooler, then red, which is cooler still. Above the red region, combustion no longer occurs, and the uncombusted carbon particles are visible as black smoke. The common distribution of a flame under normal gravity conditions depends on convection, as soot tends to rise to the top of a general flame, as in a candle in normal gravity conditions, making it yellow. In microgravity or zero gravity, such as an environment in outer space, convection no longer occurs, and the flame becomes spherical, with a tendency to become more blue and more efficient. There are several possible explanations for this difference, of which the most likely is that the temperature is sufficiently evenly distributed that soot is not formed and complete combustion occurs. Experiments by NASA reveal that diffusion flames in microgravity allow more soot to be completely oxidized after they're produced than diffusion flames on Earth, because of a series of mechanisms that behave differently in microgravity when compared compared to normal gravity conditions. These discoveries have potential applications in applied science and industry, especially concerning fuel efficiency. In combustion engines, various steps are taken to eliminate a flame. The method depends mainly on whether the fuel is oil, wood, or a high-energy fuel such as jet fuel. Flame temperature. Temperatures of flames. By appearance, it is true that objects at specific temperatures radiate visible light. Objects whose surface is at a temperature above approximately 400 degrees Celsius will glow, emitting light at a color that indicates the temperature of that surface. See the section on red heat for more about this effect. It is a misconception that one can judge the temperature of a fire by the color of its flames, of the sparks in the flames. For many reasons, chemically and optically, these colors may not match the red, orange, yellow, white heat temperatures on the chart. Barium nitrate burns a bright green, for instance, and this is not present on the heat chart. Typical temperatures of flames. The adiabatic flame temperature of a given fuel and oxidizer pair indicates the temperature at which the gases achieve stable combustion. Oxidisinoacetylene 4990 degrees Celsius. Oxyacetylene 3480 degrees Celsius. Oxyhydrogen 2800 degrees Celsius. Air-acetylene 2534 degrees Celsius. Blowtorch 2200 degrees Celsius. Bunsen burner 1300 to 1600 degrees Celsius. Candle 1000 degrees Celsius. Smoldering cigarette temperature without drawing. Side of the lit portion 400 degrees Celsius. Middle of the lit portion 585 degrees Celsius. Temperature during drawing. Middle of the lit portion 700 degrees Celsius. Always hotter in the middle. Fire ecology. Every natural ecosystem has its own fire regime, and the organisms in those ecosystems are adapted to or dependent upon that fire regime. Fire creates a mosaic of different habitat patches, each at a different stage of succession. Different species of plants, animals, and microbes specialize in exploiting a particular stage, and by creating these different types of patches, fire allows a greater number of species to exist within a landscape. Fossil record. The fossil record of fire first appears with the establishment of a land-based flora in the Middle Ordovician period, 470 million years ago, permitting the accumulation of oxygen in the atmosphere as never before, as the new hordes of land plants pumped it out as a waste product. When this concentration rose above 13%, it permitted the possibility of wildfire. Wildfires first recorded in the late Silurian fossil record, 420 million years ago, by fossils of charcoalified plants. Apart from a controversial gap in the late Devonian, charcoal is present ever since. The level of atmospheric oxygen is closely related to the prevalence of charcoal. Clearly, oxygen is the key factor in the abundance of wildfire. Fire also became more abundant when grasses radiated and became the dominant component of many ecosystems. Around 6 to 7 million years ago, this kindling provided tinder which allowed for the more rapid spread of fire. These widespread fires may have initiated a positive feedback process, whereby they produce a warmer, drier climate more conducive to fire. Human control. The ability to control fire was a dramatic change in the habits of early humans. Making fire to generate heat and light made it possible for people to cook food, simultaneously increasing the variety and availability of nutrients and reducing disease by killing organisms in the food. The heat produced would also help people stay warm in cold weather, enabling them to live in cooler climates. Fire also kept nocturnal predators predators at bay. Evidence of cooked food is found from 1.9 million years ago, although there is a theory that fire could have been used in a controlled fashion about 1 million years ago. Evidence becomes widespread around 50 to 100,000 years ago, suggesting regular use from this time. Resistance to air pollution started to evolve in human populations at a similar point in time. The use of fire became progressively more sophisticated, with it being used to create charcoal and to control wildlife from tens of thousands of years ago. Fire has also been used for centuries as a method of torture and execution, as evidenced by death by burning, as well as torture devices such as the iron boot, which could be filled with water, oil, or even lead and then heated over an open fire to the agony of the wearer. By the Neolithic Revolution, during the introduction of grain-based agriculture, people all over the world used fire as a tool in landscape management. These fires were typically controlled burns or cool fires, as opposed to uncontrolled hot fires, which damage the soil. Hot fires destroy plants and animals, and endanger communities. This is especially a problem in the forests of today, where traditional burning is prevented in order to encourage the growth of timber crops. Cool fires are generally conducted in the spring and autumn. They clear undergrowth, burning up biomass that could trigger a hot fire should it get too dense. They provide a greater variety of environments, which encourages game and plant diversity. For humans, they make dense, impassable forests traversable. Another human use for fire in regards to landscape management is its use to clear land for agriculture. Slash-and-burn agriculture is still common across much of tropical Africa, Asia, and South America. For small farmers, it is a convenient way to clear overgrown areas and release nutrients from standing vegetation back into the soil, said Miguel Pinedo Vasquez, an ecologist at the Earth Institute Center for Environmental Research and Conservation. However, this useful strategy is also problematic. Growing population, fragmentation of forests, and warming climate are making the Earth's surface more prone to ever larger escaped fires. These harm ecosystems and human infrastructure, cause health problems, and send up spirals of carbon and soot that may encourage even more warming of the atmosphere and thus feed back into more fires. Globally today, as much as 5 million square kilometers, an area more than half the size of the United States, burns in a given year. There are numerous modern applications of fire. In its broadest sense, fire is used by nearly every human being on Earth in a controlled setting every day. Users of internal combustion vehicles employ fire every time they drive. Thermal power stations provide electricity for a large percentage of humanity. The use of fire in warfare has a long history. Fire was the basis of all early thermal weapons. Homer detailed the use of fire by Greek soldiers who hid in a wooden horse to burn Troy during the Trojan War. Later, the Byzantine fleet used Greek fire to attack ships and men. In the First World War, the first modern flamethrowers were used by infantry, and were successfully mounted on armored vehicles in the Second World War. In the latter war, incendiary bombs were used by Axis and Allies alike, notably on Tokyo, Rotterdam, London, Hamburg, and, notoriously, at Dresden. In the latter two cases, firestorms were deliberately caused, in which a ring of fire surrounding each city was drawn inward by an updraft caused by a central cluster of fires. The United States Army Air Force also extensively used incendiaries against Japanese targets in the latter months of the war, devastating entire cities constructed primarily of wood and paper houses. The use of napalm was employed in July 1944, towards the end of the Second World War, although its use did not gain public attention until the Vietnam War. Molotov cocktails were also used. Used as fuel, setting fuel aflame releases usable energy. Wood was a prehistoric fuel, and is still viable today. The use of fossil fuels, such as petroleum, natural gas, and coal, in power plants supplies the vast majority of the world's electricity today. The International Energy Agency states that nearly 80% of the world's power comes from these sources. The fire in a power station is used to heat water, creating steam that drives turbines. The turbines then spin an electric generator to produce electricity. Fire is also used to provide mechanical work directly in both external and internal combustion engines. The unburnable solid remains of a combustible material left after a fire is called clinker if its melting point is below the flame temperature, so that it fuses and then solidifies as it cools, and ash if its melting point is above the flame temperature. Protection and prevention. Wildfire prevention programs around the world may employ techniques such as wildland fire use and prescribed or controlled burns. Wildland fire use refers to any fire of natural causes that is monitored but allowed to burn. Controlled burns are fires ignited by government agencies under less dangerous weather conditions. Firefighting services are provided in most developed areas to extinguish or contain uncontrolled fires. Trained firefighters use fire apparatus, water supply resources such as water mains and fire hydrants, so they might use A and B class foam depending on what is feeding the fire. Fire prevention is intended to reduce sources of ignition. Fire prevention also includes education to teach people how to avoid causing fires. Buildings, especially schools and tall buildings, often conduct fire drills to inform and prepare citizens on how to react to a building fire. Purposely starting destructive fires constitutes arson and is a crime in most jurisdictions. Model building codes require passive fire protection and active fire protection systems to minimize damage resulting from a fire. The most common form of active fire protection is fire sprinklers. To maximize passive fire protection of buildings, building materials and furnishings in most developed countries are tested for fire resistance, combustibility and flammability. Upholstery, carpeting and plastics used in vehicles and vessels are also tested. Where fire prevention and fire protection have failed to prevent damage, fire insurance can mitigate the financial impact. Restoration. Different restoration methods and measures are used depending on the type of fire damage that occurred. Fire damage can be performed by property management teams, building maintenance personnel, or by the homeowners themselves. However, contacting a certified professional fire damage restoration specialist is often regarded as the safest way to restore fire-damaged property due to their training and extensive experience. Most are usually listed under fire and water restoration, and they can help speed repairs, whether for individual homeowners or for the largest of institutions. Fire and water restoration companies are regulated by the appropriate state's Department of Consumer Affairs, usually the State Contractors License Board. In California, all fire and water restoration companies must register with the California Contractors State License Board. Presently, the California Contractors State License Board has no specific classification for water and fire damage restoration. Hence, the Contractors State License Board requires both an asbestos certification as well as a demolition classification in order to perform fire and water restoration work. Glossary. Residential fire and accidental fire in a domestic setting. Bibliography. Khaki, Samir. Community involvement in and management of forest fires in Southeast Asia. Project Firefight Southeast Asia. Archived from the original on February 25, 2009. Retrieved 13 February 2009. Porn Kai, 2009. Population and building factors that impact residential fire rates in large U.S. cities. Applied Research Project. Texas State University. TX State. Edu. Lenthal, Lee B. Holden, Zachary A. Smith, Alistair M.S. Falkowski, Michael J. Hudak, Andrew T. Morgan, Penelope Lewis, Sarah A. Gessler, Paulie Benson, Nate C. Remote sensing techniques to assess active fire characteristics and post-fire effects. International Journal of Wildland Fire. 319-345. DO 10.1071, WFO 5097. Cosman, Admiral, Sacred Fire. In Thursday, January 13, 2011.